Hello and welcome to the Unit 7 Section 5 video on coordinate quadrilaterals. So in the past couple of sections we've been talking about special types of parallelograms and the relationship that we have between rectangles, squares, and rhombuses with parallelograms. Well, to prove that a quadrilateral is a parallelogram, what of the parallelogram conditions must be met? To prove that a quadrilateral is a rectangle, it must be a parallelogram and meet one of the rectangle conditions. To prove a quadrilateral is a rhombus, it must be a parallelogram and then meet one of the rhombus conditions. And then to prove a quadrilateral is a square, you have to show that it is both a rectangle and a rhombus, of course, after showing it's also a parallelogram. So how does all of this relate to one another? Well, here is a table of all the conditions and the things that you have to look for. So we're going to check off what conditions must be met for any one of these different types of parallelograms. So for a parallelogram, you must check off one of these conditions. If you meet one of these conditions, then you have a parallelogram. But you may very well also have a rectangle, okay? And that occurs if we also check off one of these two rectangle conditions. Now for a rhombus, we know a rhombus is also a type of parallelogram, so we can check off any of these parallelogram conditions, or we can also say it's a rhombus if we can add one of these three conditions to it. Now for a square, we have to show that first of all, it's a parallelogram, so we have to meet one of these conditions. And we have to show that it's also a rectangle, meaning we meet one of these two conditions. And we have to show that it is a rhombus, meaning that we check off one of these three conditions. So a square is as specific of a parallelogram as you can get. It meets all of the criteria. The rhombus meets all but two of the criteria, a rectangle meets all but three of the criteria, and a parallelogram meets all but the last five criteria. So hopefully this is one place where you can kind of have all of your information to determine what type of parallelogram you have. Now the figure here summarizes these findings. A polygon can also be classified more generally by the names it is connected to above it, but it cannot necessarily be classified by the names that is connected to below it. So for example, you see that we have a parallelogram here at the top. A parallelogram can more specifically be a rhombus or a rectangle. And if it is also both of these things, then you have a square. So squares are always rectangles. Squares are always rhombuses. Squares are always parallelograms, but a rectangle is not necessarily going to be a square. A rhombus is not necessarily going to be a square. A parallelogram is not necessarily going to be a rhombus, rectangle, or square. So that's how we look at it. And we are going to expand on this figure a little bit as we move into the last section here. So now let's move on to talking about parallelograms in the coordinate plane. So let's take a look at this example. Three vertices of parallelogram ABCD are A at this coordinate, B at this coordinate, and D at this coordinate. We want to find the coordinates of the fourth vertex, C. So since ABCD is a parallelogram, both pairs of opposite sides must be parallel. So we are going to ensure that we have this. So we're going to start by graphing the given points. So we've got A at 1, -2. So this is where A is going to be. We have B at -2. Oh, I'm sorry. Yeah, -2, 3. So there's B. And then we've got D at 5, -1, which would be here. And we can connect these lines. So let's connect these vertices here. Okay. So now that we have these marked, let's find the slope of AB. Well, we can do that just by counting because we have a graph. So rise 1, 2, 3, 4, 5 over run negative 1, 2, 3. So our slope is going to be negative 5/3. So let's start at D and count the same number of units. So we go 1, 2, 3, 4, 5, 1, 2, 3. And then we plot right there. Okay, and this is our vertex C. So let's finish connecting these. B to C here, C to D there. So this should be a parallelogram. And to verify that, we are going to verify that BC is indeed parallel to AD. So BC is here, AD is here. So the slope of BC is 1, 1, 2, 3, 4. So rise of 1, run of 4, 1/4. The slope of AD, well, let's see, that's rise 1, run of 4, so this is also 1/4. So the coordinates of vertex C, the coordinates of vertex C is going to be 2, 4. And that's what we were set out to show. Now, let's talk about proving parallelograms in the coordinate plane. We want to show that quadrilateral ABCD with the given vertices is a parallelogram by using the given information. So, to show that it's a parallelogram, we need to show that AC has the same slope as, or I should say AB has the same slope as CD, and that BC has the same slope as DA. So let's start with the slope of AB. So that's going to be 7 minus 2 over negative 2 minus negative 3, which is going to be plus 3. And that's going to give us 5. Okay, we're just using the slope formula, y2 minus y1 over x2 minus x1. Now, the slope of CD should be the same if it is to be a parallelogram. So, we do negative 1 minus 4 over 1 minus 2. And that's going to give us negative 5 over negative 1, which is also going to be 5. So this part checks out. Let's try the slope of BC. Well, when we do that, we're going to do 4 minus 7 over 2 minus negative 2. That's going to be negative 3/4. So the slope of DA should be the same thing. So we got 2 minus negative 1, which is 2 plus 1, negative 3 minus 1, and that's also going to be negative 3/4. So this one checks out. So since both pairs of opposite sides are parallel, ABCD is a parallelogram by definition. For B, we want to show that this is a parallelogram by stating that opposite sides are parallel and congruent. So let's show that they're parallel first by calculating their slope. So let's do the slope of GH. And that's going to be 3 minus 2 over 4 minus negative 2, which is 4 plus 2, which gives us 1/6. The slope of JF should be the same thing. So we got negative 2 minus negative 1, which is going to be negative 2 plus 1, over negative 4 minus 2. That gives us 1/6 as well. There's a little bit more detail in the filled out notes. So take a look at the filled out notes where everything's typed in, and you'll get a little bit more detail there. Now, we've shown that the opposite sides are parallel. Now we need to show that they are congruent, which means we need to show that they are the same length. So to find the length of GH, we are going to use the distance formula. Square root of y2 minus y1 squared plus x2 minus x1 squared. So we have 4 minus negative 2 squared plus 3 minus 2 squared, and that's going to give you the square root of 37. Now let's take a look at the measure of JF. So again, we've got the square root of negative 4 minus 2 squared plus negative 2 minus negative 1 squared, and that is also going to be the square root of 37. So they are the same length. Since JH and JF have the same slope, GH is parallel to JF. Since GH is equal to JF, GH is congruent to JF. So therefore, we have a parallelogram. All right. Let's move on to taking a look at the properties of squares. We're going to verify the properties of squares. So the first thing we're going to do in this figure, to show that this is a square, we are going to show that AC and BD, AC being here and BD being here, our diagonals are congruent. To do that, you are going to use the distance formula again. So we have 2 minus negative 1, which is 2 plus 1 squared, plus 7 minus 0 squared, and that's going to equal the square root of 58. So we would want BD to be the same thing. So we've got the square root of 4 minus negative 3, which is 4 plus 3 squared, plus 2 minus 5 squared. That is also the square root of 58. So since AC equals BD, then we can say that AC is congruent to BD. So our diagonals are congruent. That's one stipulation. You have to have congruent diagonals to show that it's a rectangle. So essentially what we showed here is that it is a rectangle. All right, so now we need to show that AC and BD are perpendicular, because that would show that it is a rhombus. Okay, so we have the slope of AC. That is going to be 7 minus 0 over 2 minus negative 1, which is 2 plus 1. That gives us 7/3. So if the slope of BD is to be perpendicular, we would want it to be negative 3/7. So let's see if that's what we get. We have 2 minus 5 over 4 minus negative 3, which is 4 plus 3, and that does give us negative 3/7. So they are perpendicular. For step 3, we want to show that AC and BD bisect each other. So to do that, we're going to use the midpoint formula. So the midpoint of AC is going to be -1 plus 2 over 2. That's x1 plus x2 over 2. And then we got y1 plus y2 over 2, which is 0 plus 7 over 2. And so we get 1/2 7/2. So we want to see if the midpoint of BD is the same. And if it is, then they bisect each other. So the midpoint of BD, we're going to have -3 plus 4 over 2. And we've got 5 plus 2 over 2. And that gives us 1/2 7/2. So since the midpoints of both are in the same place, then they bisect each other. So that's the properties of squares. Okay, we are going to close off this section by identifying special parallelograms in the coordinate plane. And this is going to be something that you're doing a little bit more of on your own. So we are going to use the diagonals to determine whether a parallelogram with the given vertices is a rectangle, rhombus, or square. And we'll give all the names that apply here, okay? So first we want to determine if ABCD is a rectangle. To do that, we know that the diagonals have to be the same length. So let's use the distance formula to see if they are the same length. So AC is equal to the square root of 8 minus 0 squared plus 6 minus 2 squared. And that's going to give us the square root of 80, which is 4 times the square root of 5. Now, the distance of BD, that's going to be 5 minus 3 squared plus 2 minus 6 squared. That gives you the square root of 80, which is also 4 square root of 5. Actually, let me correct myself here. 2 minus 6 squared, it's actually the square root of 20, which is 2 times the square root of 5. So since our diagonals are different lengths, since 4 square root of 5 does not equal 2 square root of 5, then ABCD is not a rectangle. And we can even go further than that. ABCD is also not a square. Since ABCD is not a rectangle, let me erase that. It is also not a square. Okay, so now all that's left is to determine if it is a rhombus. And we do that by seeing if the slope of the diagonals are perpendicular. So the slope of AC is going to be equal to 6 minus 2 over 8 minus 0, which is 1/2. So we want the slope of our other diagonal, BD, to be the negative reciprocal of that. 2 minus 6 over 5 minus 3, that's going to give you -2. So since AC is perpendicular to BD, then ABCD is a rhombus. All right, so that's a little bit of a look at how to deal with figures when we know what the coordinates of the vertices are. Coming up in the next and final section of this unit, we are going to talk about two final types of quadrilaterals, those being kites and trapezoids.